Can folks in the chat hear me okay? Wonderful, thank you. Okay, so as always, remember to do the seating survey. This is the last day that's ever going to have to be done in this semester. This is the last live class period where people have the option to show up in person. So the exam is out and available now. The due date is Sunday at 5. I have extended office hours, some today, some tomorrow, and quite a bit on Saturday. I may be able to have some on Sunday. I don't fully know that yet. First thing this afternoon, after I get home, I am going to come up with what the schedule is going to be for those. I've already posted some set of those that I know I'm going to do, but I'm probably going to be doing more than what I already posted. So I will try to get that information out early this afternoon. Make certain that before you take the exam that you look at the notes on how we are handling scientific notation. So the issue is that when we are dealing with equilibrium constants, when we are dealing with pH and these sorts of things, we have to have numbers that are very large or very small. And so we need to have some way to represent them. After some digging, I found a way to implement that in the Blackboard tests, but they have to be entered in a specific format, and I have that as part of the instructions of the exam, so it's available to you there. It's also in a Piazza post. I'm also going to go over it a little bit here first so that I can show you what we're doing. So this is an Excel style of representing scientific notation. That does not mean we're using Excel for anything. We're not. It's just that this is the style that I was able to get working in the test. So the idea is if you have some number, 1.234 times 10 to the minus 6 that you are wanting to represent in scientific notation, what you enter is 1.234 e minus 6. Read the e here as times 10 to the. Okay. So I have it set so that the e can be either upper or lower case. I have it set so that if you need a plus sign at some point, that you can either enter the plus sign or leave it off, but it needs to be in this format specifically. Additionally, if you have, I'm going to, in every one of these cases, I'm going to specify the number of significant digits you need to use. You have to use exactly that number of significant digits in your answer. So if I tell you to report this number to 2 significant digits, you have to do it as 1.2 e minus 6. Okay. There are no spaces on either side of the e. Okay. I tell you which units your answer needs to be in. Do not enter the unit designation. Just put in the numbers like this. Any questions on this format? I am allowing wiggle room in whatever the last reported digit is. It depends on how big that wiggle room is allowed. It depends upon the question specifically, but the last digit that's reported allows you a range of answers. Not all of the answers are going to be reported in the scientific notation. I tell you specifically which ones need to be. So pH, for example, that would be kind of silly to do that in scientific notation. So you enter that one just normally. Okay, if there are no questions on that, do we have any other logistical questions about the exam or anything else about the class before we get on to content? Seems like a no. Okay. So I've got 3 muddiest points that came up. One of them came in to me privately, but it's a good enough question. I decided to go ahead and talk about it today. I'll go through these and then we'll open up the questions to whatever people want to talk about most. So one of them was that in the titration lab, we had said that pH equals pKa at the midpoint of the titration because the log of the concentration ratio is 1. So, and the question is this a valid assumption whenever the ratio is 1 to 1? So this is based on the Henderson-Hasselbalch equation, where pH equals pKa plus the log base 10 of the concentration of A minus over concentration of HA. And when these two concentrations are the same, this ratio becomes 1. The log base anything of 1 equals 0, and so the pH equals pKa. And so the question we have here is that, is this a valid assumption whenever the ratio is 1 to 1? And within the context of this question, yes, it is valid anytime you do this. The only cases where this is not going to be the case is when the concentrations of the acid and the conjugate base are extremely small. So you wouldn't imagine adding, nanomolar amounts of the acid in the base and be able to instantly get the pH all the way down to whatever the pKa is. But in any sort of realistic system where we have reasonable quantities of A minus and HA, yes, the Henderson-Hasselbalch equation works. And it works best, in fact, closest to 1, to the ratio being 1. Does anybody have any questions on that aspect? No. Okay, second point here was looking at my video on how to calculate the pH at various points along a titration curve. And I have a summary at the end of that video that explains the thinking process of deciding what to do at each various point. And the idea is to calculate the concentration of the acid and its conjugate base. If they're between 1 to 9 and 9 to 1, use the Henderson-Hasselbalch equation. And somebody was confused about what this last part meant. Let's set it up a little bit and talk about the first part first, calculating the concentration of the acid and its conjugate base. And then we'll get to what the second part is. So if we have a weak acid, strong base titration, we have our standard acid reaction for HA. But this reaction, that's the operative reaction in determining the equilibrium, has a problem for us because we are adding hydroxide to this system, OH minus, and there's no OH minus in this reaction. So we need to figure out what to do with that piece of information. What do we do with the strong base component? The general idea is that if you have HA in solution, and you add OH minus to it, well, OH minus is a strong base by itself. So it's going to pull off the hydrogen from the acid to produce A minus, aqueous, plus H2O, liquid. And so we use this reaction here to pre-shift the equilibrium based upon how much base was added. So you start with a certain number of moles of HA, and you start with 0 A minus. So this is going to be some number that you start with. You start with your number of moles of A minus initially is going to be 0 because you're starting the titration without having already added any base yet. And so what happens then, I'm going to mark these as initial, so comma I. After we add base, we add an amount of OH minus to the system. Our new number of moles of HA is going to be the number of moles of HA we started with minus the number of moles of hydroxide, because each bit of hydroxide pulls a hydrogen off of HA, resulting in turning it into A minus. So the amount of hydroxide we add is the amount that gets subtracted from how much HA we start with. Then the number of moles of the A minus becomes 0, how much we started with, plus the number of moles of hydroxide that we added. So the idea here is that for each molecule of hydroxide that is added, each ion of hydroxide that's added, it makes one molecule of A minus. Okay. So once you have those two new values, the number of moles of HA, number of moles of A minus, you put them over your new volume to get your new initial concentrations. So concentration of HA is going to equal that number of moles of HA over your volume total, and you do the same thing for A minus, number of moles of A minus over the volume total. And so those are the starting values that we use to determine what we do to find the pH at that point along the titration. So, remembering again the Henderson-Hasselbalch equation, pH equals pKa plus log base 10 of concentration of A minus over concentration of HA. This ratio here is what determines whether we can use the Henderson-Hasselbalch equation or not. If that ratio is between 1/9 and 9/1, so that one of these constitutes 10% of the total amount of A that you have, and the other one constitutes 90%. If you're in between that range, then the Henderson-Hasselbalch equation is considered accurate enough to use. If you are outside of that range, so if the A minus concentration is 1% of the HA, or vice versa, something like that, then you need to use an ICE table, because the Henderson-Hasselbalch equation makes an assumption. The Henderson-Hasselbalch equation says for our equilibrium, HA aqueous plus H2O liquid, equilibrium with A minus aqueous plus H3O plus aqueous. If we do this as an ICE table, we have some amount here. So this is our initial concentration of HA. This is our initial concentration of A minus. And we have this at 0. Minus X, X, X. HA minus X, A minus, plus X, and X. The Henderson-Hasselbalch equation assumes that this is negligible and that this is negligible. And that is only a good approximation if the ratio is in this range. So, if you find that you are needing to calculate the pH along a titration and your A minus and HA concentrations are not inside this range, not only do you know at that point that you have to do an ICE table, you also know that you should not be ignoring the X's in that calculation. So you can save some steps by going ahead and taking into account those X's when you move to doing the ICE table. Okay, so I went through that relatively quickly, and I know that that was kind of dense with information. Was there anything in that explanation that you felt like you missed that it would be helpful to go back over? Okay. So the private question that I got, which I think is good enough to go ahead and call it a muddiest point and come back to it, is I've mentioned a couple of times that the examples we've done in class have been a weak acid, strong base titration. So weak acid, strong base. But there's nothing really different about the concepts of what you use if you are instead doing a weak base, strong acid titration. You just have to make sure that you are tracking whether you are looking at pH or pOH, and you have to be tracking whether you have concentrations of hydronium or concentrations of hydroxide. And then also which of the standard reactions you're using. Are you using the standard base reaction or the standard acid reaction? But this question that I got was a good one, which is, what about the Henderson-Hasselbalch equation in this? The Henderson-Hasselbalch equation talks about when you're in this region here, the pH equals the pKa plus the log base 10 of the base to acid ratio. Well, here, our buffer region is up on the base side, and we're dealing with a pKb instead of a pKa. So the question then becomes, what do we do in terms of Henderson-Hasselbalch, since what we have is a pKb? So let's look at that a bit. The easiest thing to do is to think about the Henderson-Hasselbalch equation from the perspective of, if we're changing it to a base situation, how do we change everything to be the base version of it? So pH is going to become pOH, pKa is going to become pKb, and our log base 10 is going to become another log base 10 of something, but let's figure out what it is. For the standard acid reaction, we have HA plus H2O equilibrium with A minus plus H3O plus. For the standard base reaction, we have B plus H2O is an equilibrium with HB plus OH minus. So here we have the product over the reactant. So here we want to have product over reactant as well. So this is going to be HB plus over B. And so once you do this, then everything works just like you're used to. So if you're doing a calculation for a weak base strong acid titration in the buffer region here, then you use the base version of the Henderson-Hasselbalch equation right here. Anybody have any questions about that? Okay, well, those are the muddiest points that came up on Piazza. So I am now happy to talk about anything anybody feels like they would like refreshers on, or to go further depth into, whatever people would like. If you would like, I can also pull up the Piazza list of topics that I posted last week or something. And we could go down those and see what people would like most. Yes? Okay, we can do that. I'll switch to the PC. Whoops. And okay, here. So I have a comment here. There's been some confusion about what happens at the midpoint versus the equivalence point. So yeah, let's do that before we call up the topic list. Okay, so in a titration, so this is a weak acid, strong base example. We have the volume of, say, NaOH that's added. We have the pH. We have the equivalence point, which is the point of fastest rise, right here. This is known as the equivalence point. And this is the point at which the number of moles of added base equals the number of moles of the weak acid that you started with. In this case, where we have the buffer region in the acidic portion, we are going to end up with a pH greater than 7. So 7 is going to be down here somewhere. The half equivalence point, which means that we have added, so here we have the half equivalence point, which is also known as the midpoint. And that is the point where the amount of sodium hydroxide that has been added equals half of the initial HA. And let's think about what that means. If we think of this as being, as following the reaction I described earlier, where the hydroxide pulls the hydrogen off of HA, then that means that our number of moles of HA is going to be half as much as we started out with. And it's also going to equal the number of moles of A minus that we now have, because that's what it turned the HA into. So when that is the case, we have the concentration of A minus equals the concentration of HA, and we are at the very middle of the buffer region where the Henderson-Hasselbalch equation says that this log goes to 0, and so the pH equals the pKa. So, so that is what, that's the difference between the equivalence point and the midpoint. So the question here, does that assume a 1-to-1 stoichiometric ratio? Well, so if we think about the standard acid reaction, HA plus H2O, equilibrium A minus plus H3O plus, this stoichiometric ratio is always 1-to-1. Because if we have a polyprotic acid, let's say phosphoric acid, so we have H3PO4 plus H2O, we don't have this turn into immediately PO4 3 minus. It happens in steps. It becomes H2PO4 minus plus H3O plus. The second step, H2PO4 minus plus H2O, in equilibrium with HPO4 2 minus plus H3O plus. And the final step is PO4 2 minus plus H2O in equilibrium with PO4 3 minus plus H3O plus. And when we look at the titration curve for this compound, you have one buffer region, an endpoint, an equivalence point, a second buffer region, another equivalence point, and third buffer region. And then there is an equivalence point up here, but you just don't see it because you're running up against the highest pH you can get because of water. And so when you're looking at the equivalence point here, that is the equivalence point for the first reaction. And it is still a 1-to-1 ratio. And in this buffer region, it is equal amounts of this and equal amounts of this. The second equivalence point is now this reaction happening, and you've taken off the second proton. And the midpoint here is equal amounts of this and equal amounts of this. So, so each individual deprotonation step is still a 1-to-1 ratio. What about Lewis acid-base reactions where we don't have hydrogen to be our indicator? So we have not done anything about non-aqueous, non-proton transfer titrations. We could imagine what that would end up doing, but there's no way I'm going to hold you responsible for figuring that out. Yeah. So in terms of titrations, all we are looking at is currently aqueous systems and proton transfers, so Bronsted-Lowry stuff. Okay. So any further questions about these kinds of, the structure of a titration curve, equivalence points, midpoints, polyprotic acids, things like that? No. And since what we are doing is titrating typically a weak acid with a strong base, it makes sense to pick a strong base that only has a single hydroxide, rather than something like a calcium or magnesium salt or something where there are multiple hydroxides. It just makes the math easier. The solubilities are higher, so we just use sodium hydroxide or potassium hydroxide as a matter of course for these kinds of titrations. And if we're going the other direction here with a weak base but a strong acid, we would use a strong acid like HCl or nitric acid, which is monoprotic, rather than something like sulfuric acid, which is a strong acid but is diprotic. So the idea is that usually you only have one unknown that you're dealing with. That's the weak acid or base that you're dealing with. It's the thing that's in the beaker that you're adding stuff to, and you pick something convenient that's strong to go in the burette. Okay, so there's another question here. What are we going to need specifically in regards to salt hydrolysis? I was confused when they gave the formation of salt reaction in Newton, but it was just a bunch of extraneous info. Okay, so the main thing to know about about salt hydrolysis. So let's see. So the main idea is when you have a salt, let's see, let's look at sodium phosphate. What you should do is look at the ions that you get when it dissociates. So this is a solid. It's in equilibrium with 3 Na plus, aqueous, and PO3, but let's let PO4 3 minus, aqueous here. Okay. And what you do then is you look at what do these ions do on their own. Sodium I hope you can look at that and recognize that sodium here is the conjugate acid of a strong base. That strong base is NaOH. When you put sodium hydroxide into water, it fully dissociates into sodium ions and hydroxide ions. And so since that is a strong base reaction, it's a one-way arrow, not an equilibrium. And so the Na plus OH minus, putting sodium ions into solution will not shift the equilibrium back to the left because it is a one-way reaction. So the sodium does nothing in terms of affecting the pH. The phosphate, on the other hand, I hope you can recognize from our example earlier, right here, is the conjugate base of a weak acid. And so if we put phosphate into solution, that phosphate is going to make the solution basic. You're going to have the reaction PO4 3- plus H2O is in equilibrium with HPO4 2- plus OH-. And so here we see how the solution becomes basic. And then this could even pull off another hydrogen, depending on concentrations, to make the solution even more basic, and so on. So that's the general idea of what you're doing with salts, is that you are you look at the components of the salt and you see which of them might have some effect on the pH and which ones won't. And that comes down to identifying if this is a conjugate acid or a base of something, and then look at the conjugate, is it a strong or a weak acid or base? I do know that Newton had a lot of questions that were, what happens when you mix a weak acid and a strong base? What happens if you mix a weak acid and a weak base? And all of this list of things, and it's made it sound like there's this list of rules you need to memorize. And I disagree with that approach to it. My view on the approach is you treat the reactions independently. And so you look at what the components individually do, and then do they interact with each other or not? That's about it. All right, anything else on this before I pull up the list of topics? Okay. All right, we'll share screen here. So we are, where am I? My brain hit a speed bump. Here we go. So in this post, we have the list of topics here at the bottom. I will leave everything but solubility up for now. I don't know if that's legible to people. Pull up the chat window here so I can see their questions. Okay, so Aiden wants to do a buffer example problem. We can certainly do a buffer example problem. And then we'll get to Shane's question here in a moment. So a buffer example problem is largely going to be similar to doing a titration problem and just looking at the region around the half equivalence point. So you're in a regime where you're going to use the Henderson-Hasselbalch equation. The one kind of extra thing that could go into this would be identifying, if you have a target pH, identifying what you would use in order to generate the to generate the buffer that you want. So usually in a buffer type situation, you're wanting to buffer at a specific pH. Let me switch to document cam again and take a look. Okay, so the idea is this is a buffer region of the titration curve. That is the region where we can use the Henderson-Hasselbalch equation, and so we do it. I've written this about 4 times already, but it's good to write it enough that it's sort of second nature what it is. So let's suppose we want to have a buffer where the pH equals, actually let me call up a list of pKa values. So okay, so let's suppose that we want to have a pH that's going to be around 3.30. And so if you are given a list of candidates, what you do is you look at the pKa's of those candidates and find the candidate whose pKa is closest to this pH. And so looking at a list that I just pulled up, I see that nitrous acid, HNO2, has a pKa of 3.37. Okay. So, and if that is the closest in the list that you have to 3.30, this is the one that you would use. So now let's figure out what exactly we would do. So HNO2 plus H2O is in equilibrium with NO2 minus plus H3O plus. So we see what the conjugate base is, NO2 minus. And so we are going to make our solution such that we have some amount of HNO2 and we have some amount of NO2 minus, which we probably would get from something like sodium nitrite. Okay. So let's then further suppose that, so what this means now is if we look at our Henderson-Hasselbalch equation that we know something about this ratio. So 3.30 equals 3.37 plus log base 10 of NO2 minus over HNO2. Ran out of space. So we have minus 0.07, minus 0.07 equals log base 10 of this ratio. If we raise both sides to the power of 10, we have 10 to the negative 0.07 equals our ratio of NO2 minus to HNO2. See what 10 to the minus 0.07 is. Calculator. There's my calculator. So 0.07, change sign, 10 to the power, and we want our ratio to be 0.851. And so then if we are told that the amount of nitrite that we want in the system, so the NO2 minus plus HNO2, if we want our total concentration of the nitrite that we're dealing with to be, say, 0.40 molar, then we can combine these two pieces of information to find the individual concentrations we're wanting to make. So we could solve this for one of the two. So NO2 minus equals 0.40 molar minus concentration of HNO2. And so we have 0.40 molar minus HNO2 concentration over our HNO2 concentration equals this 0.851 ratio that we came up with up here. You now have one equation with one unknown. You solve for that unknown, and then you can plug that value back into either this equation or this equation and find the other concentration that you wanted. So this kind of problem is a very common problem in chemistry labs. What you do, what happens is that you need a buffer at a particular pH that determines the ratio, and you need it to have a certain buffer capacity, which means you need the total concentration of the components to be at some threshold level. And so then you use those two pieces of information to find what concentrations you need to make the solution be. So does that kind of problem here make some sense? All right. Okay, so another question. They would say that A plus B forms salt C, and the KAB for the dissociated salt is blank. What is the pH? And the solutions that formed the salt were just a bunch of info that really just confused the whole thing. Yeah, I have no idea about that one, Shane. So if you can maybe either post that particular question to Piazza or send an example that has some details, that one has me a little confused. Okay, so there's one here describing the acidity of metal hydrates. So the idea here is that most metals, when they are in solution, so maybe a manganese, no, let's not do manganese. What do we want to do? We'll do iron, iron 2+. When iron is in water, there is a Lewis acid base reaction where water molecules associate with the iron ion. And so we end up with a bunch of water molecules that are attached. Like this, usually 4 or 6 of them that are attached. The whole thing is going to still have the 2+ charge. But the fact that the waters are attached to the iron means that the iron is withdrawing some of the electron density from the water molecules themselves. And so if it's removing some of the electron density from the water, that means that the hydrogen-oxygen bonds are slightly weaker. And so as a result, it is easier than for normal water for an H+ to leave. And so you end up with a deprotonated metal hydrate. And that makes the overall solution of a metal ion slightly acidic. Now, this is a concept that we've introduced in terms of what is going on with it, but we haven't really done any specific calculations with it. So the only thing I'm really holding you responsible for on this is understanding the general mechanism of why this solution gets more acidic when there are metal ions dissolved in water. Okay, what else can we talk about? Let me reshare. Whoops, I actually need to, nope, let's close that up. Let me share the screen. So anything else on this list, or shall I shift on, sorry, it's moving. Move on down so you can see the solubility stuff. Okay, let's take a look down at the solubility stuff. Oops, and coupled equilibria. I know earlier in the week there was confusion about relating KSPs to molar solubility. I hit that pretty hard on some earlier days, but if there are people here who are still confused about that, that could be a good topic to take a quick look at. Minimum required reagent to result in precipitation. Okay, we can do that. So the idea for a precipitation reaction is that for whatever your KSP is, let's say we've got aluminum sulfate. So aluminum's plus 3, so we need 3, 2, something like that. So in order for there to be an equilibrium, meaning in order for there to be some solid that is present, you need to have enough of the material to meet the equilibrium constant conditions. So 2Al 3 plus, no, yeah, aqueous plus 3 SO4 2 minus aqueous. So if you have, let me actually look up let me switch back to the document cam, and I'm going to look up the KSP for this particular compound. Aluminum sulfate. Well, this will actually be a very good one because the value I have found is not a KSP. It's something that we can turn into a molar solubility, so we can go through a bunch of different aspects of the problems at the same time here. So looking it up, I see that the solubility of this is 36.4 grams of Al2SO4 in 100 mils of water. So let's first turn this into a molar solubility. So that we need it in 1 liter, so 1,000 mils in 1 liter. And we need to go from grams to moles. So the page I am on has the molar mass. So we have 342.15 grams of the aluminum sulfate in 1 mole. And so we then get a molar solubility of 36.4 divided by 100 times 1,000 divided by 342.15. So we get a molar solubility of 1.06 molar. Now, if we look at an ice table for this, we find Al2SO4 2 2Al3 plus, 3SO4 2 minus, and we look at it dissolving. Two X, 3X, 2X, 3X, we find that our KSP equals 2X squared times 3X cubed. And so this is now going to be 4 times 27 times x to the 5th. And we know what x is because that's the molar solubility here. The molar solubility is how many moles of this dissolves. And if we included the x here, we have it because of the stoichiometric coefficient is 1, we do a minus x. So this is going to equal 4 times 27 times 1.06 molar to the 5th, and we get our KSP. So we get 4 times 27 times 1.06 to the 5th, close parentheses, and we get 144.5 for our KSP. Now, let us, taking this from what we had a moment ago. So we started looking at this because we wanted to do a problem about the minimum reagent required to result in precipitation. Let's suppose that we have in solution 0.2 molar of aluminum 3+ that we got in there by some other means. It's like maybe aluminum nitrate or something that dissolved the aluminum in there. And we want to know how much sulfate we would need to add in order to precipitate out aluminum sulfate. So to answer that question, we have to say that we are going to, we have to look at our KSP. Is going to be the concentration of the Al3+ squared times the concentration of the SO4 2 minus cubed. We have our KSP value from up here, 144.5. We know how much of the Al3+ we have, that's 0.2 molar. And so now we just have our unknown here, SO4 2 minus cubed. So we just solve for that to find out what concentration of this we need to add in order to start precipitating the aluminum. So 144.5 divided by 0.2 equals SO4 2 minus cubed. And so SO4 2 minus is going to equal 144.5 divided by 0.2 and take the cube root. We would need 8.97 molar, which is pretty darn high. So the answer might be you can't do it. We'd have to see. What's that? Did I not do the 0.2 right? Oh, I didn't square it. I didn't square it. Right. Is that what you're saying? Yes. Okay, thank you. Right, let me try that again. 144.5 divided by, parentheses, 0.2 squared, close parentheses, equals that. And now take the cube root of that. That's even worse. We would need 15.3 molar. So unlikely to be able to precipitate that out of this particular solution. Okay, so that is how you would do that kind of problem. So minimum reagent to result in precipitation, and along the way, we got to talk about the relationship between KSP here and the molar solubility X. We have about 15 minutes left. Anything anybody would like some more work on? If not, we can call it early today. Okay, so for unknown concentrations, we use the ICE table and include the stoichiometric coefficient to the power. For unknown concentrations, so if you're doing, yes, I would imagine in most cases that's the case, unless you're talking about an acid-base reaction where you can sometimes short-circuit that with a Henderson-Hasselbalch equation. If you're talking about concentrations having to do with solubility, then yes, an ICE table is the best way to go about it. KSP value then with no given KSP and only raise concentrations to the power. Oh, okay, I see what you're saying. So I think that's getting at this sort of discomfort a lot of people have with this expression here, where it looks like we're kind of double, let me switch so people can see what I'm talking about. I think this comes from sort of the discomfort with this kind of expression here, where it feels like we're using the 2 coefficient in 2 different places and the 3 in 2 different places here, because they're coming from different things. The 2 coefficient comes from the fact that when the reaction proceeds this way, you get 2 moles of Al3 plus for every 1 mole of this, and you get 3 moles of sulfate for every 1 mole of this. The square and the cube come from the structure of the equilibrium constant itself. And so, so when you are trying to relate how much dissolves and figure out the KSP as a result of it, then yes, you're using the 2's and the coefficients in 2 different places for 2 different things here. But when you are given an actual concentration, yes, you do not include a coefficient here because you are given that concentration. The idea is that if you're not given the concentration, but you're given how much of the reaction goes, then you have to use the 2 as a coefficient to figure out what that concentration is. So this value here is this value here, is the idea. Okay, so does that address your question there, Shane? So question about office hours this afternoon. Let me take a quick look. I will be having some office hours this afternoon. So I have a meeting from 2:30 to 3:30, but from probably about 1:30 to 2:30, I will maybe like 1:45 to 2:30, I'll be online. And then for a little while after 3:30, I will be online as well. I haven't actually posted the link you need for that yet. I will get that posted as soon as I get home to Newton. I will have significantly more office hours tomorrow, and then a lot of them on Saturday as well. I will post as much about that as I know this afternoon as quickly as I can when I get home. Okay, well, if there aren't any other questions, thank you all. Can't say I'm looking forward to going 100% virtual after Thanksgiving break, but it is, that's unfortunately what we have to do. I really would like it if you guys can let me know how it ends up working and if there's anything I can do during the synchronous sessions that we're going to be holding over Zoom to make it more effective to you. I'm not sure exactly how I'm going to do it. I kind of would like to be using the .cam like I have here, but I don't have one of those at home. I'm not sure I'm going to be able to get on campus to do it. So I will figure out what technology I will use, and I would love feedback on what's effective and what's not. Thank you all, and good luck on the test. Yes.